Hi, everybody. Welcome back. We're going to go into section 2.3, which is really all about function notation. So, right now we've just talked about how one variable is a function of another variable. Another way of looking at functions is a rule that just sends an input to a unique output. And sometimes this rule can assign the outputs kind of randomly, or sometimes there's a formula behind them. And so we're going to be looking at a case where there's a formula behind these functions. And which requires this notation. So when we see this, we let f of x be 2x plus 5. So what this says is that f is a function that takes an input, x, and sends it to an output. The output is 2x plus 5. So the input value is always in whatever the parentheses is. And to get the output, we substitute whatever's in here, and we substitute x, and that will be the output. So for example, f of 3 is just going to be 2 times 3 plus 5. Okay, and that's 6 plus 5, which is 11. Okay. Down here, f of 0 would be 2 times 0 plus 5, which would be 0 plus 5, which is 5. Okay. Now, sometimes the input value doesn't have any numerical value, and that's okay. We do the same thing. So if the input value is x plus 6, the output value will be 2 times x plus 6 plus 5. Okay. And then if we want to simplify it, we can just go ahead, we distribute the 2. This will be 2x plus 2 times 6 is 12 plus 5. And then this 12 plus 5 is 17. So this would be 2x plus 17. F of minus x, I think it would be 2 times minus x plus 5. And this would just be minus 2x plus 5. Okay. So sometimes the output will be a number, sometimes it will just be an algebraic expression depending on what the input value is. So that's what it is about. So it's just substitution right now. You're substituting whatever is in the parentheses. So let's do another example. F of 0 in this case, if f of x is defined this way, f of 0 would be 0 minus 1 over 0 plus 3. So this would be negative 1/3. F of 1 would be 1 minus 1 over 1 plus 3. That would be 0 over 4. And 0 divided by any non-zero number is always going to be 0. So we can just write this as 0. F of x plus 2, do the same. This is an algebraic expression, but we do the same substitution. X plus 2 minus 1 over x plus 2 plus 3. And x plus 2 minus 1 is x plus 1, and 2 plus 3 is 5, so this would be x plus 5. Okay. We try to do the same with negative 3. We try to do this, we get negative 3 minus 1 over negative 3 plus 3. Okay. So we'll have a negative 4 on top, and we'll have a 0 in the denominator. And whenever we can't divide by 0. Okay, whenever we have a 0 in the denominator, we say that's undefined. So this is undefined. Okay, so negative 4 over 0, that is not a number. It's undefined. Here, f of 4a, this would be 4a minus 1 over 4a plus 3. And we can't really simplify this anymore. The 4's do not cancel because 4 is only a factor of this term. 4 has to be a factor of everything in the numerator and denominator for it to cancel. So we just leave it like that. F of 1 over x would be 1 over x minus 1 over 1 over x plus 3. Okay. We could leave it like that. We wanted to. We could also, if we wanted to, we could multiply both sides by both the top and bottom by x, and then this would be 1 over x times x is 1 minus 1 over x. And then this would be 1 plus 3 over x. Okay. But you can see it doesn't really help us that much. So actually, I'm sorry, this would be the x, and this would be 3x. Okay. So this would probably easier just to leave it like this. Okay. Let's look at another example. The next page. Now here, this is f of x is equal to 10. So this is a function which we call a constant function. It takes every input. The output is always 10, no matter what the input is. So f of, there's nothing to substitute in here. The output's always 10. So f of 7 is 10, f of negative 5 is 10, f of 3x plus 1 is 10. Okay, this is an example of a constant function. Okay. All right. Now, if we bring graphs into this, so when we can graph a function where the graph is always defined by this equation y equals f of x, which means the y coordinate is whatever we get when we plug the x coordinate into f of x. So now, in this case, we do not have a formula for this, but we do have a graph. Okay, so let's, for example, the point 2, 3 is on the graph. So this means, this is equivalent to saying that f of 2 is equal to 3. Okay, so that's why f of 2, we can look at this and say what 3 is. Basically, to find these function values, they give us an x value, we look at the corresponding y value. So for negative 2, we look on the graph and see where x is negative 2. Well, that's right here. And we can see the point here is negative 2, 0, right? So that means the y coordinate is 0. Okay, so that's what the function value is. F of 0, well, we look and see what is, where x is 0. That's right here. Here we have the point 0, negative 2. Okay, so now we have the negative 2 is the output. So 0, so that corresponds to this point. F of 1, well, when is x equal to 1? It's right here. We have the point 1, 0. Okay, so the y coordinate is 0. F of 3, f of 3, if we go up here, we're at this point, and it looks like at this point the graph kind of levels off. This would be 3, 4. Okay, so since the y coordinate is 4, that's what f of 3 is. And then f of 5, we can see, is about the same. It's going to be, for this point is 5, 4. Okay, so this will be 4 as well. All right. So the y coordinate is the equal to the function value. The domain of the function is basically all the x coordinates on the graph, and we can see on this graph the x coordinates range from negative 3 to 6. So we can just give the domain like this. Okay. Basically, what we're saying is if the domain is between negative 3 and 6, that means if you take a vertical line, any vertical line from negative 3 to 6, it will intersect the graph. Okay, and if it doesn't intersect the graph, then it's not in the domain. So that's why, like, negative 4 would not be in the domain here. Does f of x equals negative 3? Does that have a solution? Well, this would mean, another way of asking this question is there a point on the graph whose y coordinate is equal to negative 3? Okay, and we can see down here, negative 3 is all the way down here, and there is no point on the graph on this horizontal line where y equals negative 3. Okay. So I guess another way of asking this is, so the answer is no. And another way of asking is, does the line y equals negative 3 intersect the graph? Okay, and the answer is no. Okay. All right, finally, let's talk about x and y intercepts. Okay, we know how to find, in general, we know how to find the x and y intercepts. To find the x intercepts, we plug in at y equals 0 and solve for x. And to find the y-intercept, we plug in x equals 0 and solve for y. All right. Now, the only thing is, remember, f of x is the y-coordinate. Okay. So, first of all, to find the x-intercept, we set y equals 0, but y is f of x. So we set f of x equals 0. Okay. And f of x is minus 3x plus 5. Or 3x plus 15. Okay, we can add 3x to both sides, divide by 3, and we get 5 equals x. Okay. So the x-intercept would be 5, comma 0. And you can check if you plug in x equals 5 in here, you get 0. To find the y-intercept, you get x equals 0. You always set x equals 0. Okay, well, what is y? Y is going to be f of x. So basically, we just want to find what is f of 0. And f of 0 is going to be negative 3 times 0 plus 15. Okay, so f of 0 is 15. And 0, 15 represents the y-intercept. And you can actually use all this to get a graph of f of x. We can see that the graph of y equals negative 3x plus 15, we know that's a line. We can see what this line is going to look like. Here's 0, 15, and here's 5, 0. Okay. So we have these 2 points, and we can just draw the line that connects them. Okay. And sure enough, we can see the slope of this line is negative 3, and the y-intercept will be 15. Okay. You could also, if you wanted, you could plot a few more points just by plugging some arbitrary values into here for x, like 1, 2, 3, 4, and you get these corresponding points over here. All right. So practice, practice, practice. And we'll see you next time.